Tonight, we're going to talk about the most dangerous substance that might exist in our universe. Not the most dangerous substance we have ever made. Not the most dangerous substance we have ever found. The most dangerous substance that physics itself will allow. It is called strange matter, and if it exists, a piece of it smaller than a grain of sand could, in principle, convert this entire planet into a copy of itself. Every mountain, every ocean, every atom of the ground beneath your bed. Here is what makes this so unsettling. Strange matter would not destroy the Earth with an explosion. It would not burn it or shatter it. It would simply touch it, and everything it touched would stop being ordinary matter and become strange matter too, which would then touch more of the planet, which would then convert as well in a quiet chain reaction that nothing known to science could stop. Physicists call this the strangest scenario, and it is not science fiction. It emerged from serious calculations published in serious journals by some of the most careful minds in physics. And the strangest part of all is this. The same calculations suggest that strange matter might be the most stable substance in the universe. More stable than iron. More stable than the atoms in your body, which raises a question that has quietly haunted physics for 4 decades. If strange matter is more stable than ordinary matter, why is the universe made of ordinary matter at all? Why are you still here? By the end of tonight, you will understand what strange matter really is, why a single drop of it earned the nickname the most dangerous substance imaginable, and why, despite everything I just said, you can still close your eyes and sleep. Before we begin this journey, if you enjoy these long, deep explorations of the universe, a quick like or subscribe genuinely helps this channel grow. It is a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with something you think you already understand. Matter, the stuff of the world. The chair you are sitting on, the air you are breathing, the hand you are using to hold your phone or adjust your pillow. You learn the story in school, and the story goes like this. Everything is made of atoms. Atoms have a nucleus in the middle made of protons and neutrons, with electrons orbiting around it. And for most of your life, that story was allowed to end there. Protons, neutrons, electrons. The 3 little bricks of reality. It is a comfortable story. It is also incomplete in a way that matters enormously for tonight, because protons and neutrons are not fundamental. They are not solid little marbles. If you could shrink yourself down and look inside a proton, you would not find a smooth ball of substance. You would find a storm. A seething, boiling, violent storm of even smaller particles called quarks, held together by a force so powerful that it makes every other force in nature look gentle. Each proton contains 3 quarks. Each neutron contains 3 quarks. And here is the first fact you need for tonight. Those quarks come in different types. Physicists, in a moment of unusual playfulness, called these types flavors. There are 6 flavors of quark in our universe. They are named up, down, charm, strange, top, and bottom. 6 flavors. But look around you. Look at your room, your walls, the trees outside, the moon through your window. Everything you have ever seen, everything you have ever touched, every star in the night sky, all of it is built from just 2 of those 6 flavors. The up quark and the down quark. A proton is 2 up quarks and 1 down quark. A neutron is 2 down quarks and 1 up quark. That is the entire recipe for the visible universe. 2 flavors out of 6. So what about the other 4? What about charm, top, bottom, and the one that gives tonight's story its name, the strange quark? Why did nature buy 6 ingredients and then cook everything with only 2? That question sounds innocent. It is not, because hiding inside that question is a loophole in the laws of physics, and inside that loophole lives the most dangerous hypothetical substance ever described. To understand the strange quark, you need to understand why it is missing from your body. The 4 exotic quark flavors are not rare because they are forbidden. They are rare because they are heavy, and in the quantum world, heaviness is a kind of curse. The up quark and the down quark are featherweights, the 2 lightest quarks that exist. The strange quark is the 3rd lightest, roughly 25 times heavier than the up quark. And in particle physics, there is a rule so reliable that it functions almost like gravity. Everything that can decay into something lighter eventually will. A heavy particle is like a ball balanced at the top of a hill. Sooner or later, it rolls down. So when a strange quark is created, in a particle accelerator, in a cosmic ray collision high above your head, in the heart of a dying star, it does not stay strange for long. Within about a billionth of a second, It decays, transforming into lighter quarks, shedding its extra mass as energy. That is why your body contains no strange quarks. They were made in abundance in the early universe, in the first fraction of a second after the Big Bang, when the entire cosmos was a soup of free quarks hotter than anything that has existed since. But as the universe cooled, the heavy flavors rolled down the hill. They decayed away, leaving only up and down quarks behind, which bound themselves into protons and neutrons, which built atoms, which built galaxies, which built you. The strange quark, in ordinary conditions, is a ghost, a flicker, a particle that visits reality for a billionth of a second and then leaves. And if that were the whole story, there would be no video tonight. But in 1971, a physicist named Arnold Bodmer noticed something odd in mathematics. And in 1984, another physicist named Edward Witten, one of the most respected theoretical minds alive, took that odd little observation and turned it into a hypothesis so unsettling that it has never fully left physics alone since. They asked a question nobody had thought to ask seriously. The strange quark is unstable when it is alone or in small groups. Everyone agreed on that. But what would happen if you gathered an enormous number of quarks together? Up quarks and down quarks and strange quarks, all packed into one dense object, not in groups of three, but in one single communal mass of millions, billions, trillions of quarks with no internal walls at all. The mathematics returned an answer nobody wanted. Under those conditions, the mixture with strange quarks in it might not be unstable at all. It might be more stable than ordinary matter, more stable than iron, the most stable atomic nucleus in the universe. More stable, in fact, than anything else that exists. This hypothetical substance, this communal soup of up, down, and strange quarks, is what physicists call strange matter. And the moment you accept that it might be stable, you inherit a monster. Because in physics, stability is not a passive property. Stability is a destination. Everything in the universe is trying to reach the most stable state available to it. Water flows downhill. Hot things are cool. Radioactive atoms decay. And if strange matter is truly the most stable form of matter that exists, then every atom in the universe, including the ones you are made of, is sitting partway up a hill it has not yet finished rolling down. Ordinary matter would not be the foundation of reality. It would be a temporary arrangement. A pause. A held breath. Now I need to show you why gathering quarks together changes the rules so completely, because this is the heart of tonight's story, and it is stranger than you expect. Think about a neighborhood of houses. Each house has 3 people living in it. That is ordinary matter. Every proton and every neutron is a house, and the 3 quarks inside are roommates who are never, under any circumstances, allowed to leave. The force that holds quarks together, called the strong force, has a bizarre property that no other force shares. It does not weaken with distance. It strengthens. Pull 2 quarks apart and the force between them grows, like a rubber band that gets thicker the more you stretch it. Pull hard enough and you do not free the quark. The energy you poured into stretching simply creates new quarks out of nothing, and you end up with more houses, not free roommates. This is called confinement, and it means that in all of ordinary matter, quarks live in tiny sealed households of 2 or 3 forever. But now imagine tearing down every wall in the neighborhood. Imagine one enormous open building where all the residents mingle freely. This is quark matter, a phase of matter where quarks are not grouped into protons and neutrons anymore, but swim together in one continuous sea. And in that sea, a new rule takes over, a rule from quantum mechanics called the Pauli exclusion principle. It says that no 2 identical particles of a certain kind can occupy the same quantum state. In everyday language, identical quarks cannot all crowd into the comfortable low-energy seats. Picture a stadium. The up quarks must fill their own section, starting from the cheap seats near the field and stacking upward into the expensive high-energy rows. The down quarks must do the same in their own section. As you pack in more and more quarks of just 2 flavors, you are forced to seat them in higher and higher energy rows, and the total energy of the system climbs and climbs. But if you open a 3rd section, a strange quark section, something remarkable happens. Some of the quarks sitting in the punishingly high rows of the up and down sections can convert into strange quarks and move to the empty, low-energy rows of the new section. Yes, the strange quark costs more to make because it is heavier. That is the price of the ticket. But the seat it gets is so much cheaper, so much lower in energy, that in a large enough stadium, the trade pays for itself. The whole system ends up with less total energy than before, and less energy means more stability. That is the entire secret of strange matter, and you now understand it better than almost everyone you will ever meet. In small numbers, strange quarks are a waste of energy, and they decay. In enormous numbers, in one wall-free communal sea, strange quarks are at a discount, and the mathematics suggests the universe might prefer them. A blob of this stable quark sea, small enough to hold in your hand, at least conceptually, is called a strangelet. Remember that word, because the rest of tonight is about what a strangelet would do if it ever touched the world you live in. Hold on to the stadium picture, by the way, because it will quietly answer questions for the rest of the night. It explains why the lone strange quark decays. A single household cannot benefit from a section it cannot fill. It explains why small clumps are fragile and giant ones might be eternal. Discounts belong to crowds. And it explains something lovely about the everyday world too. The reason the chair beneath you holds its shape, the reason your hand does not pass through the table, is that same exclusion principle, the same refusal of identical particles to share a seat. The rule that props up your furniture is the rule that might, at the bottom of the deepest stadium in the universe, prefer a different kind of matter altogether. Physics uses one rulebook for everything. It just plays very different games with it depending on the size of the field. Before we get to the drop that converts a planet, let me pause and give you the honest picture of where this idea stands, because I promised you at the start that this is not science fiction, and I meant it. The strange matter hypothesis, the idea that quark matter containing strange quarks is the true most stable form of matter, has never been proven. It has also never been disproven. It sits in a strange twilight that physics reserves for its most stubborn questions. The calculations involved are among the hardest in all of science, because the strong force is so powerful that the usual mathematical shortcuts physicists rely on simply stop working. When theorists compute the energy of strange quark matter, the answer depends sensitively on quantities that are not precisely known. Turn the dials one way, and strange matter is comfortably stable, and our entire universe is quietly waiting to fall into it. Turn the dials another way, and strange matter is unstable, and the whole idea evaporates into a historical curiosity. Nature knows which it is, we do not, and that uncertainty is not a flaw in this story, it is the story. Because everything you own, everything you love, every grain of sand on every beach on Earth is composed of a form of matter that physics cannot yet promise is the final, safest arrangement of reality. Sit with that for a moment. The ground beneath you feels permanent. The mathematics says, perhaps. So now, let us do the thing you came here for. Let us take the hypothesis seriously and follow it all the way down. Suppose strange matter is stable. Suppose, somewhere, a strangelet exists. A droplet of communal quark soup, perhaps the size of a bacterium, perhaps the size of a dust mote, drifting through space. It is almost unimaginably dense. A strangelet the size of a poppy seed would weigh as much as a loaded cargo ship, and unlike almost everything else in the universe, it is not fragile. You cannot burn it. Fire is chemistry, and chemistry is the gentle art of rearranging electrons. A strangelet does not care about electrons. You cannot smash it. Smashing is the art of breaking the bonds between atoms, and a strangelet has no atoms. It is held together by the strongest force in nature, operating at full power across its entire body. A strangelet is, in a very real sense, indestructible by any means available to human beings. Now bring it here. Let it fall, gently, silently, into the Pacific Ocean at night. No flash, no sound. It sinks, because it is millions of times denser than water, and on its way down it brushes against a single molecule of water. This is the moment. This is the entire catastrophe, contained in one collision too small to see. The strangelet touches an oxygen nucleus. And here is the crucial, terrible elegance of it, because the strangelet is more stable than the nucleus. More stable meaning lower in energy. The encounter is not a fight. It is an invitation. It is a ball meeting the edge of a cliff. The nucleus is absorbed. Its protons and neutrons dissolve, their walls torn down, their quarks joining the communal sea. Some of those up and down quarks convert into strange quarks, taking the cheap seats in the stadium, and the energy difference, the height of the fall from ordinary matter down to strange matter, is released as heat and radiation. The strangelet is now very slightly larger, very slightly heavier, and every bit as hungry as before. Hungrier, actually, because a larger strangelet has more surface, and more surface means more contact, and more contact means more nuclei absorbed per second. It touches 2 more nuclei, then 4, then thousands. Each absorption releases energy, and each absorption grows the drop. There is a name for a process that feeds itself this way, a process whose product accelerates its own production. It is called a chain reaction. The strangelet sinks through the ocean, converting as it falls, growing from the size of a dust mote to the size of a raindrop, of a marble, of a boulder, glowing now with the released energy of every nucleus it has eaten, and it settles into the seabed and keeps going, down into the crust, into the mantle, toward the iron heart of the planet, converting everything it meets. And the terrifying thing, the genuinely unprecedented thing, is that no law of physics steps in to stop it. Every other catastrophe you can imagine has a limit. Fires exhaust their fuel, explosions dissipate, even nuclear bombs burn through their material in a flash and are done. But for a stable strangelet, the fuel is matter itself. The Earth is the fuel. And when the process finally ends, sometime later, whether that is hours or centuries is genuinely debated, the thing left orbiting the sun where your home used to be is a smooth, hot, unimaginably dense sphere of strange matter roughly 100 meters across. The entire planet, every city, every ocean, every mountain range, all 6,000 billion tons of it, compressed into a ball you could walk around in an afternoon if there were anywhere left to stand and anyone left to walk. That is what physicists mean when they say a single drop could convert the entire planet. Not destroyed, convert. The Earth would not be gone. It would be translated, atom by atom, into a lower, quieter, more stable dialect of matter. The universe's preferred spelling of the word world. I am going to let that image settle, and then I am going to complicate it because this is the part of the story where most videos stop, and it is exactly where the real story begins. Everything I just described rests on one hidden assumption, an assumption so subtle that it took physicists years of argument to drag it into the light. The assumption is that the stranger wants what it touches. And it turns out that this depends on something almost absurdly mundane. It depends on electric charge. Think about what the strangelet is actually made of. Up quarks, down quarks, strange quarks. Each flavor carries a different electric charge. Up quarks are positive. Down quarks and strange quarks are negative. In the idealized picture, where the stadium seats fill evenly and every section holds an equal crowd, the positive and negative charges cancel almost perfectly, and the strangelet as a whole comes out slightly negative or close to neutral. But the strange quark, remember, is the heavy one, the expensive ticket. In a real strangelet, the strange section fills a little less than the others, which leaves the mixture with a slight surplus of positive charge. And that tiny detail, that whisper of imbalance, may be the only thing standing between you and the scenario I just described, because the nuclei of ordinary atoms are also positively charged. And like charges repel, a positively charged strangelet drifting through the ocean would push water nuclei away before they ever touched it, wrapped in an invisible electric shield of its own making, exactly the way ordinary nuclei have kept their distance from each other in every substance you have ever handled. It would also do something almost comical for a doomsday particle. It would attract electrons, dress itself in them, and become, for all practical purposes, a bizarre, ultra-heavy atom. A new element, sitting quietly at the bottom of the sea, chemically bonding with its neighbors, eating nothing. The apocalypse, neutralized by static electricity, but a negatively charged strangelet is another creature entirely. Negative charge attracts positive nuclei. Instead of a shield, it would carry a welcome. Nuclei would be pulled toward it, funneled into its surface, and the conversion would proceed exactly as I described, with the strangelet's growing mass deepening the attraction with every atom consumed. So the fate of the entire planet, in this hypothesis, hangs on a question that sounds like a coin flip. Does stable strange matter, if it exists, come out positive or negative? The mainstream calculations lean positive. Lean. Some models, exploring corners of the theory where the quarks pair up in exotic patterns, find negative versions possible. And so the strangest scenario survives in that uncomfortable gap. Not likely, the majority of physicists will tell you, but not closed either. And now that you understand what a strangelet would do, and what would have to be true for it to do so, You are ready for the genuinely unnerving chapter of tonight's story. Because in the year 1999, this question left the seminar rooms and the journals. It appeared, in plain language, in newspapers around the world, attached to a machine that human beings were about to switch on. The question was simple. Are we about to make one of these things ourselves? In the late 1990s, on Long Island in New York, engineers were finishing a machine called the Relativistic Heavy Ion Collider, known by its initials, RHIC. Its purpose sounds like something out of mythology, to recreate in tiny fleeting droplets the conditions of the universe less than a millionth of a second after the Big Bang. It would do this by accelerating the nuclei of gold atoms to 905% of the speed of light and slamming them into each other head-on. In those collisions, for a fraction of a second, protons and neutrons would melt, their walls would come down, and a microscopic droplet of free quark soup, the communal sea we talked about, would flicker into existence on Earth for the first time since the dawn of time. Physicists call that soup the quark-gluon plasma, and creating it was the entire point of the machine. But in 1999, as the collider approached its first run, a letter appeared in a magazine, and then articles appeared in newspapers, and the articles asked a question that sounded reasonable to any thoughtful person. If this machine is designed to melt protons and neutrons into quark soup, and if strange quarks will be created in the collisions, which they would be, then could RHIC accidentally cook a strangelet? And if strange matter is stable, and if the strangelet came out negatively charged, could switching on this machine be the last thing humanity ever does? For a moment in 1999, the strangest scenario was not a bedtime story. It was a public safety question, on the front pages, with a deadline. The laboratory did what serious institutions do. It commissioned a formal risk assessment from a group of respected physicists who went through the scenario piece by piece, and their report contains one of the most beautiful safety arguments in the history of science, an argument that does not depend on trusting any calculation, any model, or any human being. It depends on trusting the sky. Here is the argument, and I want you to follow it slowly, because it is the reason you can sleep tonight. Everything RHIC was built to do, nature has already done, countless times, right above your head. The universe is full of cosmic rays, particles accelerated by exploding stars and feeding black holes to energies that make our best machines look like wind-up toys. Among them are heavy nuclei, iron and heavier, moving at speeds our colliders will never reach. For billions of years, these projectiles have been slamming into the nuclei of atoms at the top of Earth's atmosphere and slamming into the surface of the Moon, which has no atmosphere to soften the blow. Every one of those impacts is a heavy ion collision. The Moon has been sitting in this cosmic particle beam for 4.5 billion years. Physicists did the accounting, and the numbers are ridiculous. The natural universe has already performed the equivalent of RHIC's entire planned experimental program many times over. On the Moon alone, to say nothing of every other planet, moon, and star in the galaxy. And yet, when you walk outside tomorrow night, the Moon will still be there, silver, quiet, and made of ordinary rock. It has not been converted into a 100-meter sphere of strange matter. No star in the sky has suddenly collapsed into a strange droplet after a cosmic ray strike. The universe has been running this exact experiment at higher energies than ours for the entire age of the cosmos, and the result has come back safe every single time. That is not a theory, that is an observation. The Moon is the receipt. When RHIC finally switched on in the year 2000, it ran perfectly. It created the quark-gluon plasma, one of the great scientific achievements of the century, and it discovered something poetic in the process. The primordial quark soup is not a gas, as everyone expected, but a liquid, and not just any liquid, the most perfect liquid ever observed, flowing with almost no resistance at all. The infant universe, it turns out, was a droplet. No strangelet ever appeared, at RHIC or at the Large Hadron Collider after it, despite years of searching through trillions of collisions. And there is one more twist that the risk report pointed out, a twist that flips the whole horror story inside out. Remember the stadium. Strange matter wins by being large, by having enough seats to make the strange section worthwhile. Small strangelets, the only kind a collider could ever make, sit in the worst of both worlds, too small to enjoy the communal discount, saddled with the full cost of their heavy strange quarks. Collider droplets are born unimaginably hot, 100,000 times hotter than the center of the sun, and a hot droplet boils away before it can settle into anything. To make a stable strange matter, if it can exist at all, you do not need a hotter machine or a bigger budget. You need somewhere cold, calm, and crushing. You need pressure beyond anything a laboratory can dream of, sustained not for a trillionth of a second, but for millions of years. And the universe, as it happens, has built exactly such a place. It builds them regularly, every time a giant star dies. When a star much larger than our sun runs out of fuel, its core collapses in less than a second. And the collapse is so violent that electrons are forced into protons, converting the entire core into a single ball of neutrons about 20 kilometers across. A neutron star. We will spend another whole night on those objects someday. But tonight, what matters is one number, the pressure at the center. At the heart of a neutron star, gravity squeezes matter to densities several times greater than an atomic nucleus, which is to say, several times denser than the densest material that ordinary physics builds. And nobody, and I want to be precise here, nobody on Earth knows what matter does under those conditions. It is one of the great open questions in science. The walls between neutrons, those tidy households of 3 quarks each, may simply give way. The neighborhood may become an open building. And if the deep core of a neutron star melts into quark matter, then the stadium argument switches on. With that many quarks packed together, opening the strange section is almost certainly a bargain, which leads to one of the most quietly radical ideas in astrophysics. Some of the objects we call neutron stars may not be neutron stars all the way through. They may have hearts of strange matter. And if the strange matter hypothesis is fully correct, if strange matter is truly more stable than everything else, the conversion would not politely stop at the core. It would spread, exactly as it did in our ocean scenario, eating outward through the star at nearly the speed of light, until the entire object, all 1.5 suns worth of it, had become a single 20-kilometer droplet of strange matter. Astronomers call such a hypothetical object a strange star, or a quark star. And here is the sentence I have been building toward all night. If strange stars exist, then somewhere in our galaxy, right now, there are drops of the substance we have been describing. Trillions of tons of it, glowing softly in the dark, orbiting other stars, sweeping through the interstellar night. The doomsday droplet from our thought experiment would not be a laboratory accident. It would be a natural, celestial species. So the question stops being philosophical and becomes astronomical. Can we find one? Can we look up and tell the difference between a neutron star and a strange star? The answer is almost. A strange star is held together not by gravity alone, but by the strong force itself, which means it can survive spinning at rates that would fling a normal neutron star apart. It can be smaller and denser than any neutron star of the same mass. So astronomers hunt for outliers, stars too compact, too fast, too cold for the ordinary story. And a few candidates exist. Strange little objects whose measurements sit uncomfortably at the edge of what neutron matter should allow. None is confirmed. Every candidate has an alternative explanation. But every few years, an observation appears that makes the strange matter community sit up straight, and in the era of gravitational wave astronomy, we now have a brand new sense with which to listen. When 2 of these dead stars spiral into each other and merge, the ripples they send through space-time carry the signature of what they were made of. The way the sound of 2 glasses clinking tells you whether they are crystal or plastic. Somewhere in the decades of data ahead of us, in some future merger's final chirp, the answer to Bodmer and Witten's 40-year-old question may simply arrive, unannounced, on a Tuesday. And this is where the hunt takes a turn that I find genuinely delightful, because the search for strange matter is not confined to telescope. If strange stars exist, then strange star collisions exist, and a collision between 2 strange stars would do more than ring space-time like a bell. It would shatter droplets loose. It would spray strangelets into the galaxy the way a hammer striking a wet stone sprays water. Over billions of years, those droplets would spread through interstellar space, and some of them, statistically, inevitably, would be on a path that crosses ours. Which means the question, could a strangelet hit the Earth, is not just a nightmare scenario. It is a detection strategy. Think about what a tiny strangelet would actually be. A particle with the mass of a large molecule, or a bacterium, or a boulder, compressed into a speck thousands of times smaller than an atom. When something like that arrives at the top of our atmosphere, Moving at cosmic speeds, it does not behave like a normal cosmic ray. A normal cosmic ray, a proton, hits an air molecule and shatters, its energy exploding outward in a shower of secondary particles that detectors on the ground read like fireworks. A strangelet would not shatter. It is, remember, effectively indestructible. It would punch through the atmosphere like a rifle bullet through fog, barely slowing, barely noticing, leaving a track of ionized air and disturbed molecules in a line pointing straight down. Physicists have combed through cosmic ray data for exactly such signatures, particles with an absurdly high mass for their charge, tracks too straight and too penetrating for ordinary matter to explain. A handful of anomalous events over the decades have raised eyebrows. In the 1970s and 1980s, experiments occasionally recorded strange, ultra-heavy particle candidates that were never satisfyingly identified, events with nicknames and question marks that still decorate old conference proceedings. None was ever confirmed. Every anomaly, so far, has faded under scrutiny, the way most anomalies do. But the searches continue, and they have become wonderfully creative. There is a particle detector the size of a school bus mounted on the International Space Station, and among its many quarries is the strangelet. It sifts the cosmic rain above the atmosphere, weighing each particle, waiting for one that is impossibly heavy for its size. Researchers have studied lunar soil brought back by the Apollo missions, reasoning that the moon, with no atmosphere and no weather, is a 4-billion-year-old strangelet trap, its dust a filter that has been sieving the cosmic rain since before life on Earth began. If strangelets have been drifting through the solar system, some should be embedded in that gray powder, sitting in laboratory drawers right now, waiting to be noticed as grains that weigh far too much. And my favorite search of all, seismographs. Follow the logic. A strangelet heavier than a ton, arriving at interstellar speed, would not stop at the surface of the Earth at all. It would pass through the entire planet, entering through one hemisphere and exiting through the other in about a minute, drilling a tunnel narrower than an atom, but depositing energy all along its path, a needle of heat lancing through the world. That passage would ring the planet, faintly, in a way no earthquake can. An earthquake starts at a point and spreads, but a strange crossing would be a line source, a seismic signature shaped like a spear, thrust rather than a stone dropped in a pond. Scientists have actually searched decades of global seismic records for that shape, for the sound of a bullet of strange matter passing through the earth beneath our feet. They found candidate events. They confirmed none. But pause on the image itself, because it is one of the most extraordinary in all of physics. Somewhere in the archives of the world's earthquake monitors, there may be a squiggle, a faint line of ink from some quiet afternoon decades ago, recording the moment a droplet of the most dangerous substance in the universe flew through the planet, harming nothing, noticed by no one. And you will reasonably ask, harming nothing, after everything I told you about conversion and chain reactions. This is where the two halves of tonight's story finally connect, and where the fear, examined closely, begins to dissolve. A strangelet moving at cosmic speed is moving far too fast to eat. Conversion requires contact, capture, absorption, a slow embrace, not a collision at 100 kilometers per second. A fast strangelet punches through atoms without ever holding one. For the doomsday scenario to unfold, a strangelet would have to arrive slowly, settle gently, and be negatively charged, and it would have to exist in the first place, and strange matter would have to be stable at small sizes, and each of those requirements is its own coin flip weighted towards safety. Multiply the probabilities, and the monster grows faint indeed. And above all of the calculations stands the same silent witness as before. The Earth is 4.5 billion years old. It has been sailing through the galaxy's debris, its rains of dust and particles and wandering fragments, for its entire life, and it is still here, still ordinary, still stubbornly made of protons and neutrons. So is the moon, so is the sun, so is every planet ever photographed and every star ever catalogued. 4.5 billion years of exposure is the greatest safety trial ever conducted, and the result, everywhere we look, reads negative. Which brings us, finally, to the deepest question hiding under everything tonight, the one I planted at the very beginning and left growing in the dark. If strange matter really is the most stable form of matter, the lowest valley in the entire landscape, the destination toward which all things tend, then why is the universe made of ordinary matter at all? Why did the Big Bang, which cooked the cosmos through every temperature and passed through the quark soup phase itself, not simply settle everything into strange matter from the start? Why does anything as fragile, as provisional, as energetically extravagant as a proton exist? Why are you here? The answer is one of the most beautiful ideas in physics, and it explains far more than strange matter. The answer is that the universe does not always find its lowest valley. It finds the nearest one. Picture a ball rolling across a hilly landscape in the dark. It rolls downhill, always downhill, and eventually it comes to rest in a valley. But the landscape has many valleys, and nothing guarantees the ball found the deepest one. It found the first one. And once it is resting there, it would need a push, a large, specific, coordinated push to climb out of its valley and travel to a deeper one, and no such push is coming. Physicists call this a metastable state. Not truly stable, but stable enough, trapped behind an energy barrier, resting in a valley that is not the bottom of the world. Here is what that means for ordinary matter. When the universe cooled after the Big Bang, the quark soup froze quickly, and it froze into the arrangement that was easiest to reach, not necessarily the arrangement that was cheapest to maintain. It froze into protons and neutrons, small, tidy, 3-quark households. For the universe to correct that choice now, for a chunk of ordinary matter to convert into strange matter on its own, dozens of quarks would need to transform their flavor simultaneously, in the same place, at the same moment, a coordinated quantum leap of absurd improbability. Physicists can estimate the waiting time for such a fluctuation, and the number is not merely longer than the age of the universe. It is longer than the age of the universe, multiplied by itself many times over. A number so large that writing its digits would fill more space than the observable cosmos contains. Ordinary matter, in other words, may well be a mistake the universe made in its first microsecond, a ball resting in the wrong valley. But it is a mistake locked behind a wall that time itself is too short to climb. Left alone, your atoms will outlast every star. The only shortcut over the wall would be a seed, an already existing droplet of strange matter arriving from outside. Which is precisely why the strangelet scenario carried such peculiar horror, not because it would destroy the world, but because it would correct it. And now you can see the entire architecture of tonight in a single view. Strange matter is not really a story about an exotic particle. It is a story about the suspicion, written into our best equations, that reality as we know it is provisional, that the matter of your body is not the ground floor of existence, but a mezzanine, a comfortable landing on a staircase that continues downward into the dark. Physics has met this suspicion before. In other forms, there are serious theories in which empty space itself, the vacuum, is metastable, resting in its own, not quite lowest valley, and the strange matter question is a small, tangible rehearsal of that far grander vertigo. We live in a universe that may be unfinished, and everything we have ever loved is built from its beautiful, long-lasting, possibly temporary first draft. There is one more room in this house I want to show you before we turn out the lights, and it may be the most surprising one of all, because when Edward Witten wrote his famous 1984 paper, the paper that turned strange matter from a curiosity into a field, he was not actually trying to invent a doomsday substance. He was trying to solve a completely different mystery, one you have almost certainly heard of. He was trying to explain dark matter. By the 1980s, astronomers had a serious accounting problem on their hands. Galaxies were spinning too fast. The stars at their outer edges were orbiting at speeds that should have flung them off into intergalactic space, unless every galaxy was wrapped in a vast halo of invisible mass, 5 times more of it than all the visible stars and gas combined. Something was out there, holding the galaxies together, emitting no light. Nobody knew what. Nobody knows for certain to this day, and Witten noticed that his strange matter idea offered an answer of almost scandalous economy. Suppose, he said, that when the newborn universe cooled out of its quark soup phase, the freezing was not perfectly clean. Suppose that as ordinary matter crystallized out, countless droplets of the original quark soup were trapped, squeezed, and stabilized, like bubbles of ancient air sealed in Antarctic ice. If strange matter is stable, those primordial droplets, he called them quark nuggets, would still exist. They would be heavy, dark, compact, and almost entirely invisible. They do not shine, they barely interact, they simply drift and gravitate. Which is, word for word, the job description of dark matter. Follow the thought to its strangest conclusion. If Witten's original idea had been right, then dark matter, the invisible substance that outweighs the visible universe 5-1, would be made of exactly the material we have spent tonight fearing. The halo of our galaxy would be a swarm of strangelets. The most dangerous substance imaginable would not be rare. It would be the majority of all matter in existence. And the ordinary atoms of stars and planets and people would be the exotic minority, a bright film of foam riding on a dark ocean of strange matter. It is a breathtaking inversion, and for a while it was taken very seriously. The idea has since fallen from favor, for honest reasons. Detailed calculations suggest the primordial droplets would have evaporated in the heat of the young universe before they could grow large enough to survive, and searches for their signatures, in gravitational lensing surveys, in ancient mica, in the seismic records of the Earth, and even instruments left on the Moon, have all come back empty. Most physicists today expect dark matter to be something else. But notice what the episode reveals about the strange matter hypothesis. It is not a fringe nightmare invented to frighten people. It is a serious, flexible, deeply motivated idea that some of the finest minds in physics have tried to build the universe out of. The same mathematics that whispers of planetary conversion also volunteered, politely, to solve the biggest missing mass problem in cosmology. Ideas of that caliber do not come along often, and physics has learned to keep them close, even when it cannot prove them, especially when it cannot prove them. And in the decades since, theorists have kept renovating the house. They discovered that at the almost unimaginable densities inside a compact star, quark matter may do something even stranger than being strange. The quarks may pair up, the way electrons pair up in superconducting metals, locking their colors and flavors together into a single, glassy, frictionless quantum state. In such a phase, the accountancy of the stadium changes yet again, and some versions of the theory find that these paired states are the true, deepest valley of matter, with charges and properties that soften the doomsday scenario even further. The frontier keeps moving. But the central question, Bodmer's question, Witten's question, the one that survived the newspapers of 1999 and the empty detectors of every collider since, still stands exactly where it has stood for 40 years, unanswered, patient, and pointed directly at the ground beneath your feet. What is the most stable form of matter in the universe? Because whatever it is, that and not our familiar periodic table, is the true default setting of reality. Everything else, no matter how permanent it feels, is an arrangement the universe has merely not gotten around to changing. Before we walk back up out of the deep, I want to take you to two more places. One is a scene I owe you, and one is a star that may already be whispering the answer. First, the scene. I told you earlier that a strangelet settling into the Earth would convert the planet, and I moved past the moment quickly because there was so much road ahead of us. But this is a 2-hour journey, and you deserve to see it properly, the way the physics actually paints it, because the details are stranger and more cinematic than any summary. So return with me to the Pacific, to our impossible gentle visitor, negatively charged, freshly settled into the seabed, and let us watch with the eyes of physics. The first thing to understand is that the conversion is not free. Every nucleus the droplet absorbs falls from a higher energy valley into a lower one, and the difference does not vanish. It is paid out immediately, as heat and radiation. Physicists can estimate the payout. Converting a single kilogram of ordinary matter into strange matter would release something on the order of the energy of a small nuclear weapon. A single kilogram. Now scale that up. The Earth has about 6 trillion kilograms. The total energy released in converting the whole planet would exceed the output of the Sun over centuries, all of it emitted from one growing point in the crust. So the quiet chain reaction would not stay quiet for long. Within hours or days of serious growth, the region around the droplet would be glowing, then boiling, then radiating with the fury of a newborn star buried in the ground. The oceans above it would flash to steam, the atmosphere would be stripped and scattered. And here is the detail that always stops me, the conversion front itself, the actual boundary where the world becomes a strange matter, would probably remain microscopic in thickness, a skin thinner than an atom advancing on a wall of light. Ordinary matter on one side, the final draft of the universe on the other hand, and a line between them narrower than anything a microscope could see. The planet would not be eaten the way fire eats a forest, raggedly, at the whim of wind. It would be translated smoothly, from the inside out, in an expanding sphere of finality, and from a distance, from the moon say, the Earth in its last days would be beautiful, a blue world developing a white-hot star at its heart, brightening, simplifying, and shrinking over weeks or centuries depending on whose equations you trust, down to that final 100-meter droplet, hotter than the surface of the sun, gradually cooling in the dark, wearing the orbit the Earth used to wear. It would even keep the moon. The mass at the center barely changes, so the moon would continue to circle its converted parent faithfully for billions of years, tides pulling on an ocean that no longer exists. I am not telling you this to frighten you. I am telling you because tonight is about looking directly at the largest ideas physics contains, and this is one of them, the recognition that matter itself has a bottom floor, and that the distance between our floor and the bottom one can be measured in sunlight. And remember, always, the width of the door this scenario must pass through, a stable, strange phase, and stability at small sizes, and negative charge, and a slow, gentle arrival, 4 independent locks in the observable universe. Everywhere we have ever looked shows all 4 still bolted. The scene you just watched has, as far as 14 billion years of cosmic history can testify, never played anywhere, even once. That is the safest kind of monster there is, one whose cage is the entire visible universe. Now for the whisper. In our tour of strange stars, I told you astronomers hunt for outliers, for dead stars that are too small, too light, or too cold for the ordinary story. And I want to show you what one of those outliers actually looks like, because a candidate exists that has made the strange matter community lean forward in their chairs. In the constellation of the southern sky, there is a supernova remnant catalogued with the unromantic name of a telescope survey, and at its center sits a compact object that astronomers weighed and measured with unusual care, using its distance, its temperature, and the light of its surface. The measurement returned numbers that should not belong together. The object appears to have a mass well below what any known process comfortably makes, lighter than the lightest neutron stars we understand how to build, packed into a radius so small that ordinary neutron matter struggles to explain the combination. When theorists laid the measurements against their equations, the ordinary models strained. But one family of models fit the numbers gracefully, almost eagerly, the strange star models, the ones in which the object is not a ball of neutrons at all, but a single self-bound droplet of strange quark matter, held together by the strong force itself, able to be smaller and lighter than gravity alone would ever allow. Is it proof? No. The measurements carry uncertainties. The distance could be off. The atmosphere of the star could be fooling us, and science has been burned before by beautiful outliers that dissolved under better data. But it is exactly the shape that the first real evidence would take: a quiet paper, a strange pair of numbers, a dead star in a distant nebula that refuses to fit. And there are other whispers. Pulsars, the spinning lighthouses of the dead star world, occasionally glitch. Their clockwork rotation suddenly jumps, as if something inside the star slipped and reorganized. The pattern of those glitches encodes the interior, the way the rattle of a shaken gift encodes what is in the box, and some theorists argue that certain glitch behaviors fit better if the deep interior contains exotic quark phases. Gravitational wave detectors, meanwhile, have already recorded mergers involving compact objects whose masses sit awkwardly in the gap between the heaviest neutron stars and the lightest black holes, and each such event tightens the mathematics that describes matter at its densest. None of it is conclusive. All of it is converging. The instruments being built right now, the next generation of gravitational wave observatories, the X-ray telescopes that measure the radii of dead stars to within a city block, will shrink the hiding places year by year. The question that Bodmer asked in 1971, in a paper almost nobody read at the time, has become one of the sharpest questions in modern astrophysics, and it is entirely possible, perhaps even likely, that people alive today will hear it answered. Either matter as we know it is the true ground floor of reality, and the strange quark is forever a guest, or somewhere in tonight's sky, Among the stars you could see from your own window, the final form of matter is already shining. And before we leave the whisper of the sky and turn for home, spare a moment for the humans in this story, because the Strangelet episode changed something permanent in the way our species thinks. When the worry surfaced in 1999, it arrived as a letter from a concerned reader to a science magazine, asking, in effect, whether physicists were quite sure they were not about to end the world. A famous theorist wrote the reply, and in trying to be reassuring, he mentioned the strangest possibility by name, judged it not plausible, and moved on. The newspapers kept the name and dropped the judgment. Within weeks, the end of the world had a machine, an address, and a start date. It would be easy to tell that story as a fable about media panic, but the physics community drew a deeper lesson from it, and it is a lesson worth carrying beyond physics. When the possible harm is literally everything, the ordinary arithmetic of risk breaks down. A 1 in a million chance of losing a coin is nothing. A 1 in a million chance of losing every coin, every hand that ever held a coin, and every future that would ever mint one is not nothing and cannot be waved away with confidence alone, however expert. So the review panels did something quietly historic. They refused to restate the safety case in theory at all. Theories have assumptions. Calculations have error bars. Instead, they rested it on the universe's own experimental record. The cosmic ray bombardment of the moon and stars, an experiment with more repetitions than humanity could perform in a billion years, whose results are visible every clear night. That style of argument, grounding safety in what the cosmos has already survived rather than in what our models predict, has since become the template for how physics answers every such fear, from micro black holes to vacuum decay. It is one of the strange gifts of the Strangelet, a hypothetical monster that never appeared, but that taught civilization how to check, honestly and humbly, whether its machines can wake monsters at all. There is a kind of maturity in that, the same maturity you practice on a smaller scale every time you take a fear seriously enough to examine it instead of merely feeling it. Physics looked its worst nightmare in the eye, line by line, moonrock by moonrock, and earned the right to switch the machine on. The machine ran. The universe, as it has for 14 billion years, declined to end. So let me gather all of tonight into one place, and let us walk back up out of the deep together, slowly. We began with the comfortable story, atoms, protons, neutrons, the 3-brick universe. We opened the bricks and found the storm inside, 6 flavors of quark where the world only ever uses 2. We asked why nature ignores the strange quark, and found that it does not ignore it at all, it merely cannot afford it in small quantities. We tore the walls out of the neighborhood and discovered the stadium, the communal sea in which strangeness stops being a luxury and becomes a discount. And we met the Strangelet, the droplet of that sea, indestructible, insatiable, and possibly more stable than anything else that exists. We dropped one into the ocean and watched it translate the world. Then we did what physics always does with its monsters. We interrogated it. We found the electric shield that a positive charge would raise, the coin flip on which the whole catastrophe balances. We watched the fear reach the front pages in 1999 and watched the moon, 4.5 billion years old, testify for the defense. We followed the hypothesis to its natural home in the crushed hearts of dead stars, and learned that the galaxy may already contain strange stars, whole suns of the substance, waiting for gravitational waves to take their fingerprints. We hunted strangelets in cosmic rays, in Apollo moon dust, in the seismic archives of the Earth itself, and found tantalizing nothing. And beneath it all, we found the real subject of tonight, the idea that outlasts every scenario, metastability, the possibility that ordinary matter is not the ground floor, that the universe froze in a hurry, settled into the nearest valley rather than the deepest one, and has been resting there, magnificently, for 13.8 billion years, protected not by stability, but by the sheer improbability of change. Here's the thing I want you to notice about that idea as you get ready to sleep. It sounds like it should be terrifying, and in the small hours it can be. But hold it up to the light and it turns over, like a coin, into something closer to gratitude. The barrier that traps our universe in its imperfect valley is not a flaw in the design. It is the design. It is the reason anything lasts. The improbability of change is why your atoms, forged in stars that died before the sun was born, have held their shape through 5 billion years of cosmic weather and will hold it for longer than there will be stars to count. If the universe corrected its mistakes instantly, there would be no mistakes and no universe worth the name, no long, slow chemistry, no planets, no oceans patient enough for life, no you lying in the dark thinking about quarks. We are not built on bedrock, we are built on a pause. And the pause is trillions upon trillions of years deep, which is as close to forever as anything real ever comes. Somewhere out there tonight, perhaps, a strange star spins in the dark, 20 kilometers of the universe's final draft, humming with the stability our world was never given. Let it spin. It is not coming here. The cosmic rays have been arriving for 4 billion years, and the tide still comes in. The moon still hangs silver over the water, and every proton in your body is exactly where it was when you started this video, resting quietly in its valley, held by a wall that time itself is too short to climb. If you enjoyed tonight's journey to the bottom of matter, a like or subscribe truly helps this channel keep making these, and it means more than you know. The universe will still be strange in the morning. Good night.